This video is going to be on the calculus aspect of calculating the moment of inertia or the mass of an object where the density is not going to be a uniform or a constant number. We see this frequently in the free response questions in AP Physics C. Okay, basically what we're going to start off with is calculating the total mass, the center of mass, and the moment of inertia for discrete objects, okay, point masses located at different places. Then we'll move up to the uniform density and then the more complicated non-uniform density objects. Okay, so taking a look at the situation where I have multiple masses. So let's say I have mass M1, M2, and M3 located at three different locations in the first quadrant. Okay, located at X1, Y1, X2, Y2, and X3, Y3. Total mass is then relatively easy. Okay, we can calculate that by simply adding the three masses together. Or if there are more, just adding all of them. Okay, M1 plus M2, etc. Okay, in math notation, we would say total mass is equal to the sum, sigma, of all the little m sub i's. Okay, to calculate the center of mass, okay, we would need to worry about both the x-axis and the y-axis, but just looking at the x-axis, we would do m1 x1 plus m2 x2, etc., divided by the total mass m, and that would give us the x location of the center of mass. Doing the same process for the y-axis, we would find the y location of the center of mass. Okay, so moving on to the moment of inertia, okay, we basically calculate moment of inertia mass by mass. Each mass has its own little moment of inertia calculated by mr squared. And if we're going to rotate about the y-axis in this case, the distance to the y-axis is simply their x coordinates. So for mass 1, it would be m1 x1 squared. Okay, for all three of them, we just keep adding again. So m1 x1 squared plus m2 x2 squared, etc. Again, in math notation, it's shown there as the sigma of m sub I x sub I squared. And so that's for discrete objects. And that's going to be important because remember, calculus is going to be the summation of all these little discrete objects. Okay, and as the limit as we go, number of objects goes to infinity, or the size of them goes to 0 effectively. So let's take a look at calculating moment of mass and moment of inertia and center of mass for solid objects when the density is uniform. Okay. In general, a three-dimensional object of mass m and volume v, density would be given by rho, the Greek letter rho, is equal to the total mass divided by volume. Okay, moving down to simple two-dimensional objects, okay, the area density would be sigma is equal to mass divided by area. And for linear objects, which most of us, which is what we're going to be dealing with, mostly because we don't really do multivariable calculus just yet, we will be doing linear stuff. And so linear density is going to be mass divided by the unit length. Okay, we use some of these letters like rho, sigma, and lambda for the reasons given up there. Okay, just remember that these are simply densities. Okay, either three-dimensional, two-dimensional, or one-dimensional. In particular, focus on the one-dimensional because that's what AP Physics C is going to be doing. Okay, so let's just look at a two-dimensional object and calculating the total mass of a two-dimensional object. Okay, so I'm going to take an arbitrary shape. Okay, we have this arbitrary shape shown in the lower right-hand corner, and we're going to basically think of breaking this mass into all these little squares of the same area. We'll just call that area delta x, delta y, or so each little square then is going to have a mass of m sub I, which is equal to the density, sigma, times that delta A, the area of that little square. Okay, so to find mass, all I have to do is add up all those little squares, sigma of m sub I. Just remembering now that sigma m sub I is really sigma delta A, or sigma delta x times delta y. Expanding this into calculus notation, assuming the delta x's and delta y's go really, really small, then we have total mass is the double integral of sigma times dx dy. Okay, I know we haven't really encountered the double integral, but it basically just means integrate along the x and then integrate along the y. That's really all that is. Okay, but we're not going to do that. We're going to go straight to one-dimensional. Okay. So to calculate the mass of a one-dimensional object, we're going to think of breaking this rod, shown in the lower right-hand corner, into little sections of width delta L. Each little section then will have a mass equal to lambda times that delta L. Okay, and then same process to find total mass, we'll just add all those things up. And because it's one-dimensional, it's a single integral of lambda dl. Okay, where lambda is the density function. Okay, in this case, it's just a constant, and we would integrate this from 0 to L. So let's see that in practice. Okay, well, actually, let's calculate the center of mass for this rod. We're basically going to call the axis of rotation, as shown in the picture, x equals 0, and we're going to integrate it all the way out to L. So remember that center of mass is calculated as 1 over m times sigma m sub I x sub I. We don't have to worry about the y-axis in this case because it's one-dimensional. So for a solid object, 1 over m is a constant. You may need to calculate that using the previous slide, but still it's 1 over m. Okay, it's a constant. So we're going to integrate from 0 to L, the lambda density function, times dl, which is basically just the mass of the object, times L, which is how far it is from the pivot point. Okay, or x equals 0 because we're not actually pivoting yet. Okay, so 1 over m, the lambda, L squared over 2, do the substitution, and we find that the center of mass is nothing more than L over 2. For an for a uniform mass, that's exactly where you would expect it to be, the center of the rod. Okay, so moving on to the moment of inertia now. Moment of inertia is the sum of mx squared. Okay, going to calculus, it's the integral from 0 to L of the mass, again, lambda dl, times L squared. Okay, how far it is from the pivot squared. Going through the process of integrating, we find that the moment of inertia is going to be 1/3 ml squared, which, if you recall, is exactly what you would get for a rod rotated about one end. Okay. If I was to do this for a rod rotated around its center, my limits of integration would be different because the center would be x equals 0. And so I would integrate from minus L over 2 to L over 2. And if I did so, I would find that my moment of inertia would be 1/12 ml squared. You should try that on your own. Okay, so moving on to solid objects that have non-uniform density. Okay, so uniform, remember, is a constant number. Okay, density is equal to mass over volume, or simply mass over unit length for a one-dimensional object. However, now we're going to be looking at density as a function of position. If it was three-dimensional, we'd be looking at f of x, comma y, comma z. But we're basically doing it in just one dimension. So lambda of x is going to be some function of x. A lot of times it's linear. Sometimes it's squared. It could be almost anything, but they'll usually stick to polynomials or powers of some form. So let's look at how do I calculate total mass. Okay, for total mass, I'm just adding up all the little sums. So I'm integrating mass. The mass is, again, nothing more than lambda dl, or whatever that function is, dl. Okay, so for example, if I have lambda is equal to some beta, some constant beta times distance from the axis, integrating that from 0 to L gives me a mass of beta L squared divided by 2. Okay? And so that's the total mass of this rod with a density function of lambda, which is linear, starts at 0, close to the origin, goes all the way out to beta at, say, 1 meter. Okay. So what does that actually look like in real life? Okay, what's a zero density object? Okay, there is no such thing as a zero density object. Okay, in reality, what they're effectively saying is it's triangular in shape, but we're pretending it's just the density is changing from 0 to some number. Okay, so to calculate the center of mass, it's the same process. Okay, it's the center of mass is 1 over m times the sum of m sub I x sub I. Changing this sigma to an integral sign, mass becomes lambda dLs. That's the mass of that little section that you see in the picture. And that's going to be beta L, okay, times the L, which is the x sub I. So I have integral from 0 to L of beta L squared dL. Okay, actually integrating it, we find that the center of mass is going to be located at beta L cubed divided by 3m, whatever that happens to be, okay, numerically speaking. Okay. Taking a look at the moment of inertia, okay, it's the same process, except we're summing mx squares. Okay, so changing the sigma when we dl basically approaches 0, then it becomes an integral. Lambda is still that function, that's beta L, and I'm going to rotate it about one end. Okay, so the moment of inertia in this case from 0 to L is lambda dl, which is our mass, times the L squared for x squared. And again, expanding that thing out, it becomes the integral of beta L cubed dl. Going through the substitution, it becomes nothing more than 1/4 beta L to the 4th. For any other density function lambda, okay, just substitute it in and integrate appropriately, okay, and you should be able to get your answer. Thank you very much.